So in this video, I'll be going over the solutions to Exam 2's practice exam. And so this discussion is going to closely mirror what the review session will be like in terms of what I'll be discussing. So for the first problem, what we have is we have a block that's being pushed horizontally against a rough wall. So the keyword rough tells you that there is friction. So you're going to have to take into account friction. And so we're pressing on the block and we're asked, does the block fall? So you can imagine taking your textbook and pushing it up against the wall. Now vary how much force you're placing on that textbook and see whether it slides or it doesn't slide. If it slides, then pick it up and try and push more force into the book and see if it doesn't slide. What you're going to find is it won't slide if you start to push on it enough. So you apply a great enough force. And so this is what the situation's going, this is the situation that's happening here in problem 1. Is the force great enough to keep the block, or from the example I just said, the book from falling down? So how many forces do we have? Well, we definitely have an applied force to the left. We know since there's a mass, there must be a weight force. Right? It's a rough wall, so there must be friction happening. And where does friction act? Friction always opposes the motion or the would-be motion of an object. So if there is enough force to hold it up, which way would the block want to fall? The block would want to go downwards. Gravity's pulling it down. The block would fall to the ground. So what would be the opposite of that direction? Well, that would be upwards. So the force of static friction is opposing the weight force. And that's specifically what keeping the block from falling, if it isn't falling. And is this all the forces? Well, the block is up against the wall, and we're pushing the block into the wall, so the block's applying a force to the wall. So by Newton's third law, the wall must be pushing back on the block. If the block's pushing on the wall's pushing on the block. So the wall is applying a normal force to the block to the right. Now, I didn't draw these vectors to scale. I just wanted to show them just to define the forces. Now, if the block isn't falling, then actually I've drawn it fairly well. Because if it's not falling, what do we know about the acceleration? That's the y direction, that's the x direction. What do we know about the acceleration in the y and x direction? Well, if it's stationary, then we know that the acceleration in the y direction and the x direction must be 0. So what does that tell us about forces? Well, if the acceleration is 0, then we know that the sum of the forces in the x direction, the sum of the forces in the y direction, must be 0. Because remember, the forces are proportional to the acceleration. So if the acceleration is 0, the sum of the forces must be 0. And likewise for the acceleration in the y direction. So that tells you how to draw the length of your vectors if you expect the acceleration to be 0. So in a problem like this, when you don't really know, it's okay if you've drawn your vectors slightly off. It's the accelerations that you do know, that's when you want to be very specific with how you draw the length of your vectors. So you know that in the x direction, you're not going to have acceleration in this problem. So you know that the applied force is going to be equal and opposite to the normal force. It's the y direction that you're not sure. That's the question mark, because you don't know what the static frictional force is. If it's the same as the weight, then the block's not going to move. But if the maximum static frictional force is less than the weight, then the block is going to fall down. There's nothing to keep it from falling down. And so that's what we just talked about. That is the approach to this problem. Does the block fall turns into, in physics terms, in these variables, is the weight force greater than the maximum static frictional force? If the weight force is, then the block falls. If the maximum static frictional force is greater than the weight force, then the block doesn't fall. And the static frictional force will be equal to the weight. So you draw your free body diagrams, you fill out your force table, and then again, when you sum the forces, after you filled out this table, so let's take it for the x direction. When you sum the forces in the x direction, you literally take this table and you substitute those values into that equation. You have negative 15 newtons, and you have the normal frictional force, Fn. Or, excuse me, the normal force, Fn. So you have Fn minus 15 newtons equals 0, because you know the sum of the forces in the x direction must equal 0 because there's no acceleration in the x direction. So literally, you're just taking this table and you're setting it equal to m mass times the acceleration, whatever that is in that direction. That's why as soon as you draw your free body diagram and you pull all of these forces and combine them into this table, you're doing all the work for you. You know, that's the bulk of your work in this problem. After that, you're just taking what you've already compiled and you're just substituting it into these equations. And so after you solve for the force, that gets you the normal force. From there, you can figure out the maximum static friction force, which is 12 newtons. And then you can figure out, well, what is the scenario? How much friction do I need for the block to not fall? So you're summing the forces in the y direction, you're setting it equal to 0, and you're determining what static frictional force do I need so that the block does not fall. And you find that it's 10 newtons. So the frictional force is less than the maximum static frictional force that we can have in this scenario, so the block won't move. And the static frictional force is going to be equal to 10 newtons because it's enough to oppose the weight that's pulling the block down. For this next problem, and this is going to be something that you are definitely going to have on the exam, you're going to be drawing free body diagrams for all of your problems. And specifically, you're going to have problems where you're just drawing a free body diagram for a situation. And so these are straight, so these scenarios right here are all straight from the note packet. These are problems that we dealt with. So these are things that you should be able to draw free body diagrams for and be able to draw the lengths of the force vectors relatively well. Meaning that the lengths are consistent in a relative manner with what is happening with the acceleration. One thing that I'll point out for this scenario here, we have motion that's along an incline or a decline. Do we use our standard coordinate system? So we must use a tilted coordinate system because the motion is along the incline. Whenever you have motion at an angle, whether it's at a decline or whether it's going up an incline, you must rotate your coordinate system so that it matches the incline. And the reason why we do that is because that forces the incline, our coordinate system, to match the motion. We have this block that's going down, right? Oh, it's at rest. It wants to go down because gravity wants to pull it down. So we have motion along this incline. And now we have acceleration, if we have it, along a certain axis. We don't have to deal with angles for acceleration, which makes the problem very difficult. And so that's the reason why we tilt our coordinate system. You only tilt your coordinate system when there is motion along an incline. Say I have a block like this along level ground, and I apply a force downwards. Should I tilt my coordinate system? And so in your head, what you should be thinking is no. This block is going to move, if it does move, along this horizontal plane. That matches what our typical coordinate system is. Y straight up, X is horizontal. So we're going to have motion already in the X direction, if we have it. So there's no reason to tilt a coordinate system, even though we have a force that's at an angle. The problem is not having forces at an angle. We have dealt with that through the past two modules. The problem is when you have acceleration at an angle. That's what's difficult to break up into components and match it up with the forces. So again, if you have motion at an incline or a decline at some angle, then you need to tilt your coordinate system to match that angle's motion. Question 3, what do we have here? So we have a satellite orbiting above the surface of Mars, experiences a gravitational force. So what you should be saying to yourself as soon as you're reading this is Newton's universal law of gravitation. That's what you should immediately be thinking when you see this problem. So we're going to use Newton's universal law of gravitation, and what we're asked to find is we're asked to find the distance that the satellite is orbiting above the surface of Mars. So this distance here, this distance d. And so this is pretty standard. You're just going to be using Newton's universal law of gravitation, the equation right here, g, which is the gravitational constant times the first mass times the second mass divided by the radius squared. The one thing that I do want to point out about this problem is what this radius means. This radius means from the center of object 1 to the center of object 2. And what that corresponds to is the center of Mars to the distance of the orbit.